Hello, and welcome back to the third video in the programming the REV into the deep starter bot. In last week's video, we finished off the teleop with finite state and using the enum to control the arm. In this week's video, we're going to show you how you can actually transfer that over to auto control instead of just the controlling the arm based on when the drivers press a specific button. So this, because the series is going kind of in line, kind of half a week to a week later than the Go Builder one, we finished the Go Builders auto already. So you can see how we have the starter bot Go Builder auto with drive methods. So what I'm going to do is I'm not going to fully go through explaining everything in super detail because otherwise this video is going to take too long. But I'm going to quickly overview mainly the drive methods because that's what's going to be similar to the Go Builder one. And then spend most of the time talk about the actual controlling the hardware that's different to the Go Builder one, like the ARM and using the state machines and the enum in auto rather than teleop. But I'm still going to cover this, the actual driving a bit, so that you don't necessarily have to go to the other video and have a look at that. But if you want more detail, that's where you should look. Okay, so to get started here, I'm going to copy the Go Builder Auto, and we're going to paste it in here, and we're going to rename it the StarterBot Auto Rev. Okay, don't worry about that. Okay, so now what we're going to do is I'm just going to remove all of this ARM code because the ARM code is going to be different, right? We're going to have to get the new ARM code out of for the Go Builder specifically. Sorry, the Rev specifically. Okay, so I've cut down all of the ARM hardware. We have the drive motors left, some constant for the driving, so that we can drive a specific distance, because this is the main difference between your teleop control and your auto control, is that you are not just taking input from the driver's joystick and just setting a motor power. In auto, you need to tell it to drive a specific distance. So let me quickly pull up. Let me see, what Chrome is this showing? I need to quickly change which Chrome I'm looking at so that I can. Here we go. Okay. FTC into the deep field. Oh, no. Field. So we're going to go to an image here quickly. So this is basically what we did in the Go Builder session, right? We looked at an example autonomous that would actually be relevant in the game this year, right? So we assume that we are starting here at this point against the wall. You always have to start against the wall, but you're allowed to start in between these two lines anyway. And what the aim is to take your preloaded sample, your yellow sample, which you can preload in your claw, and place it in the low baskets right here. So what we did and what we figured out is that you need to drive, if you start with your robot edge around here, you need to drive about 10 centimeters to this way, or because the robot's going to start on its side, you just want to drive the robot backwards 10 centimeters. So now we need to figure out a way we can actually tell the robot to drive a certain amount of centimeters, right? And so what we have to do that is we have to convert those centimeters into a metric or a unit that the robot can actually understand. It can't understand centimeters, but it does have the motor encoders inside the wheel motors that can track ticks per revolution, right? It tracks a certain amount of ticks for every time it turns around once. And we can use this to figure out how many centimeters we've traveled based on the circumference of the wheel. So basically what we have to do is we have to take the motor's wheel circumference, the motor's ticks per revolution. So how many times it ticks, it counts a tick when it spins once around. You can see I've got an example here, I think. Yeah, wait, what? Oh yes, I do. Okay, cool. So you can see I've got an example here. So basically we need the motor encoder's ticks, right? Like I said, if it rotates once, how many ticks does it read? And we also need this red line here. We need the wheel circumference because then, as you can probably see where this is going, we can figure out how many ticks the motor needs to move the robot forward a certain amount of centimeters, simply by dividing the dividing the ticks we need to travel by the circumference of the wheel. So if we go down here, so you can see here we have ticks per centimeters. We have the motor ticks per revolution, the amount of times how many ticks it reads when it rotates around once, and then the wheel circumference in centimeters, this red line, right? And then what we can do is we can take the target distance we want to travel in centimeters and multiply it by that constant, and that will give us the amount of ticks that the motor needs to travel to drive that distance. So if we go back into Android Studio, so now that I've explained kind of the theory behind that, this is basically the implementation for it. So you can see here we have the wheel circumference. You need to double check this on your exact wheels, but I think for the REV wheel, this is correct. It's a 96 millimeter wheel diameter, which is about a 30 centimeter circumference. And then ticks per revolution. This is also dependent on your motor specifically, but as far as I know, these the REV starter bot runs on the custom gearbox motors. I'm not sure what RPM. Let's look over here at the build guide. So you can see, like we've talked about in the teleop before, it's all about figuring out what hardware you have before you kind of can actually implement it. So if we go down here, assembly guide for this, we need to find the drivetrain. I don't know if they have the drivetrain in here. Drivetrain, okay. And then we need to get the custom gearbox motors. No, it doesn't tell us the exact ratio. No, okay. So what you're going to need to do is you're going to need to go here, and I don't have time to figure out where it is now, but you need to find the exact RPM, or you might actually change the RPM of your motors based because you want more speed or you want it to be slightly slower. So basically what you need to do is you need to find the RPM, and then basically how you figure out the ticks per revolution of the motor if it doesn't give it to you. If you can just find the RPM, then you sorry, you actually need the gear ratio. So you need the gear ratio because a bare motor for a REV motor counts 28 ticks per revolution. So if you have the gear ratio, say you gear it up by, or gear it down by like 5, right? So it's 5 to 1, then you just multiply 28 by 5, and that's going to give you your ticks per revolution. Okay, so once you have that value, you input it here. I'm going to leave it as this for now. I believe that's pretty similar because the RPM of the Go Builder one versus the Rev one is going to be very similar. You find your ticks per centimeter value, right? Then if you go down here, now this is something we haven't looked at before in this series, is using a method to allow you to call a function or a piece of code multiple times. So basically, this is the method. This is called a method. It's called the drive distance method, and basically what this allows you to do is to just call one line of code and tell it how many centimeters you want the robot to drive forward, and it will drive forward that many times. Instead of having to put all of this code in every time you want to drive a certain distance, you can just call this in one line of code, give it a number of centimeters to travel, and that's going to drive the robot forward that amount of distance. And if you put in a negative value, it's going to drive it backwards. So what exactly does this do? So you can see here, we find the motor target, right? The target centimeters, that get inputted here. You multiply it by the ticks per centimeter. That's the value we created before, right? And that's going to give us the amount of ticks the motor needs to travel forward for it to move that number of centimeters that you've inputted. And then what we do is we stop and reset the encoder. We set the target position to this motor target. We run them to the position. So this will actually run the motors to that target tick position, forward or backwards, depending if you put a positive or a negative value in there. And then what we're going to do is we're going to wait while that is busy happening. So this is something also that we haven't done in the teleop yet, is that we are actually waiting for the action to complete before we move to the next one. In teleop, you never want to use while loops or sleeps because that's going to block other input from the drivers. But in auto, because everything's happening like sequentially or linearly, right? They're happening one after each other. You need to wait for the one action to finish before you start the next one. So that you don't just, if you can imagine, if you don't wait, right? The example of if you don't wait, you'd be, where am I? Over here. You'd be like sitting right here, right? As you started it, as you started your program, you'd sit right here, it would start driving, flick the arm up, let go of the sample all at the same time, and then the program would just stop. Because you're not waiting for it to drive first, then flip the arm, and then let go of the sample, and then flip the arm back in. That type of thing, right? That's why you need this while loop here, to actually just wait for that. And then you can see up here, you can call it here, right? Here's the name of the method. You can just call it. You can say drive distance. And then you can see it's prompting us to input a target centimeters. So you can input any number or you can input a negative number or whatever. You can see I've already got it up here, so I'm going to delete that. So you can see how that you can easily use that to drive a certain number of centimeters. It makes it very easy to use, and no code duplicates whatsoever, which is really nice. Now, the other thing you need to do in your auto, right, not in the preload auto because you're just driving backwards, but if you want to collect another sample of the spike marks, for instance, you're going to need to turn your robot, right? So to do that, we need some way of telling the robot to turn a certain number of degrees. So if I pull up my example here again, here we go, a bit further down. So now what exactly do we need to convert degrees we want to turn, right? Say, for example, we want to turn 90 degrees we need to eventually get it down to a motor ticks that the wheels need to turn, right? And this motor tick target, the one wheel will go forward, the one wheel will go backwards, because in the drive method, we're just setting them both to positive or forward when we want to go forward and both to backwards or negative when we want to go backwards. But to turn, you need to spin them in opposite directions. So what we need to do is we need to try to find that distance those wheels need to turn in opposite directions to turn the robot that number of centimeters, or sorry, that number of degrees. So you can see here I've got another example. You can see degrees to centimeters, right? We're converting how many degrees we want the robot to turn into the number of centimeters the wheels need to travel. Because then if we can get the centimeters the wheels need to travel, we can use the exact same method and constant that we did with the drive method to turn it into a tick, right? We can say, okay, here's the degrees we need to travel, convert it into centimeters that the wheels need to travel, and then after we've got the centimeters the wheels need to travel, we can convert it into ticks the wheels need to travel, or ticks the motors need to turn, right? So to do that, you can see it says here, it says degrees to centimeters equals the turning circle divided by 360 degrees. The turning circle being this red circle here. These blue rectangles represent your wheels, and the red line is your turning circle, or the number of centimeters your wheels need to travel to turn a full 360 degrees. To find this out, you can just measure the distance between your two wheels, right? And that'll be the diameter of your circle, and then you can just multiply it by 3.14 or pi to get your circumference of that circle, which is your turning circle. And once you have this, you're just going to divide it by 360, and that's going to give you the constant you need. And then you can see down here we have wheel target position equals target position in degrees multiplied by the degrees to centimeter constant, right? So that's going to give us back that some number of centimeters that the wheel needs to travel. You can see here I've got a bit of an example. We say, let's say, for example, the red circle is 100 centimeters. The degrees to centimeters would then be 100 divided by 360, right, for a full turning circle in degrees. And then that's going to equal this 0.27, sorry. And then the input to degrees here you can see is represented by this green line. Need to turn 90 degrees. So the target wheel position is 90 multiplied 0.2 multiplied by 0.27, which then gives us 24.3 centimeters. So now that we got that, we can just input that into our one from before and get out the ticks and then just tell the wheels to go in opposite directions for that distance. So now I've talked through that, I'll show you how it was implemented in the code. So you can see here we have the turning circle. We're saying it's 40 centimeters between the two wheels, which is about what you would have on a REV starter bot between the two powered wheels, and then we're multiplying it by pi to get our turning circle. And then the centimeters per degree value is the turning circle, right? This value I just talked about, divided by 360, or the number of degrees it takes to rotate once around, or do one full rotation. So then what we do is we have this drive method down here, right? What we do is we have the same method, but it's called the turn degrees method. And instead of taking in the target centimeters, it takes in a target of degrees. Same thing applies here. If you set it to a positive number of degrees, it'll turn positive, or it'll turn that amount of degrees to the right. And if you give it a negative degrees, it'll turn that amount of degrees to the left. So what we're going to do here, you can see we're trying to find the target centimeters, this value, which is equal to the degrees we need to travel multiplied by that value, the centimeters per degree, right? And that's going to give us back the target the wheels need to travel in centimeters. So then you can see here, after that, we're getting the motor target, which is exactly the same as our drive method. It's target centimeters, which we found here, multiplied by the ticks per centimeter. And then we have the exact same thing here. We're going to stop and reset the encoders, and then we're going to set the target position. Now you can see here, here's the difference to the drive method, besides the finding of the target centimeters, is that we're going to reverse the input. You see, we're going to add a negative sign here in front of the input for the right drive motor. And that's going to mean they go in opposite directions instead. So for instance, if you input a positive number of degrees like 90, and your target motor ticks, for instance, is like 500, right? It's going to set your left motor to go forward 500 and your right motor to go negative 500, which means it's going to turn to the right. Same thing applies if you're going to the left. You're going to say negative 500, then your left drive will be negative 500, and then because you're taking the opposite value using a minus sign, it's going to say positive 500 for the right wheel, and it's going to go in the other direction. Then we're going to just run it to position again, and we're going to wait while it's busy running to position. So you can see here, we can do the same thing up in our actual code here. You can see this at override signifies this is the actual code we're running, and it needs to be after the wait for start line. Everything before the wait for start line is the initialization code. Everything after it is what happens when you press start on the program. So we can call the same method here. We can say turn degrees and say a number, right? In our target degrees. Okay, so now that we actually have run through that, how exactly do we use this in kind of sync with hardware control to enable us to actually run that auto we were talking about at the start? So what we're going to do is we're going to go into, no, wrong one. Start about teleop go builder. Okay, so we're going to go into the teleop for the, oh, sorry, not go builder. Sorry, REV. So we're going to go in here, and what we're going to do is we're just going to grab all of the hardware, right? So we have our arm motor, our wrist motor, intake servo, and the clipping gripper, right? We're going to go back in here and up by our drive motors. We're going to put in the hardware. Then we're going to come down in here, and we're going to grab all our initialization code. Okay, you can see we've got some errors here, red text, because we haven't imported the constants, the correct constants for the positions of the arms. Okay, everything is good here. We've got our drive motors initializing up here, and then our other hardware initializing here. Okay, so the other thing we need to grab is we need to grab these constants, right? All the positions of the arms and the claws. Let's put them up here with our other hardware. There we go. You can see now there are no longer red errors here. Perfect. Okay, and then the other thing we need to add is we need to take our arm state right over here. Oh, not X. And then we need to input this in right here. And then what we need to do for this is we want to say, it's slightly different control for the auto because in the teleop, what we're just doing is we're saying if the driver presses the button, we're going to change the state, and the state will handle what to set the targets of the motors, of the arm and the wrist. But in auto, we can't really do that because, like I was talking about, we need to wait for the one action to finish before we move on to the next action. So how are we going to actually do that is we need to the way you would probably want to do it normally is you want to figure out the speed of your motor, and then do a sleep based on the distance the motor is traveling. But we don't. It's difficult to do that off the bat. So the best way, and you don't want to go that fast because it often introduces some inconsistency because there's no like waiting a bit once you get to the target position. So this is something you're going to have to tune when you're testing your auto. What we're going to do is we're going to grab this statement here that sets the position of all the arms and all that. We're going to come down here and we're going to create another method down here like we have for the drive methods. We're going to say public void. We're going to say update arm position, right? We're not going to input anything and we're just going to put this code in here. And this means now what we can do, let's go back to our auto example here and what we're aiming for. We're going to go here. And we're going to say, if we're starting here, what actions do we need to complete? So basically, we need to first drive back a bit, like I mentioned at the start, drive back 10 centimeters. Then we want to flip the arm over, right? Because the arm's going to be in the initialized position. We need to flip it over to deposit out the back in the basket. So what state do we need to set it to? We're going to start with the state of initialization, right? That's the way it would start. Or actually, yeah, collect sample, same as initialization, right? That's where it's starting. And now what we want to do is, okay, let me remove the turn because we don't need the turn. We're going to drive back 10 centimeters, right? And that's going to wait until it's driven back 10 centimeters. Then we'll move on to the next thing. Now we're going to say, what did we call the arm state? Arm state, just arm state. We're going to say arm state equals deliver. Wait, what did we call this now? I am forgetting. Low basket. Oh, we called it low basket, right? We want to deliver to the low basket. So we're going to say low basket. We're setting it to the low basket, right? Okay. So set it to the low basket. Now this isn't going to wait. Oh, wait. I was showing this wrong screen. Okay, here we go. I'm back. You're back with me now. So I've changed this now to drive 10 centimeters. And what I'm doing here is I'm setting the arm state to the low basket, right? For delivery. But now this isn't going to wait for the arm to get to the low basket before it deposits. So what we need to do is we need to add a while, and then before we do this, we need to go up to the top here, and we need to add a timer in to time how long. We can use this to time how long it's been since we set the position of the arm. So what you want to say is you want to say elapsed time equals timer, or we're going to say arm timer because it's for the arm equals new elapsed time. Great. Okay. And now what we want to do is when we set the state, we're going to say arm timer dot reset, right? So we're resetting it to 0. So then we're starting from 0 when we set the arm state. And then we can time how long it has been since we set the arm state, and we will then be able to know if we can move on or not. So we're going to say while arm timer dot milliseconds, right? We always count stuff in milliseconds when doing this because seconds is too big a unit. And for the rev arm, it's probably only going to take about 600 milliseconds, which is just over half a second to move over. But it's best to start with more time and then slowly chip it down to speed it up if necessary and if you want to optimize it. So it is probably best to start with 1,000 milliseconds, which is 1 second. And then in this while loop, what we want to call is we want to say call the update arm position, right? This is the method we just created, and this will actually set the arm and the wrist motor to the correct position. Okay, so now it's going to wait until the arms move to the specific position. So the other thing we need to do is we need to come here and we need to grab the intake, right? The intake servo control. So the intake 1, if you set it to 1, it's going to pull it in, right? And if you set it to 0, it's going to spit it out. So what we want to do is directly after this, we want to spit out the sample, right, into the basket. So we're going to say intake servo dot set position to 0, which is going to start reversing the servo and spitting it out. Now again, we need to wait for this to run for a bit amount of time to actually get it out. Otherwise, it will never spit it out correctly. So the nice thing about this is we can literally just copy this, put it over here, right? It's going to reset the timer again, and then await 1,000 milliseconds. Now, we don't really need to wait 1,000 milliseconds here. 500 is probably just fine. And in this case, we don't actually have to update the arm position. We can just wait until we can just wait because the servo is going to go for that amount of time. And then directly after this, we want to set the servo to 0.5, which is going to actually stop the servo, right? So 0 reverses it, spits it out, 1 pulls it in, and 0.5 stops it. So great, now we've reversed out the sample, we've delivered it into the basket, we've stopped the servo. What do we want to do next? So for this auto, you probably just want to flip the arm down again and you could stop it there. Or you could drive here, right? You could drive all the way to this observation zone to park, or you could park here for points as well. The other option is you come and try grab here. I'm not going to show that in this video, but basically with the turn method I showed, with the drive method, and with this kind of method of waiting for each action to finish, you can actually program any type of auto by just stitching these different kind of actions together. So for this example, what I'm going to do is I'm just going to say, we're going to set the arm state, right? We're going to copy this arm state. You can see how easy it is. I can just copy that little line of code. And run it. And maybe something I can quickly just show, which I think would be very useful, because even this, right, it's like 5 lines of code. And if you have to copy that every time you want to move the arm, you're going to have a really long auto. So one thing you can do is you can say public void set arm state. Sorry. Put the brackets, right? And then what we want to take in is we want to say arm state, state. Okay. And then we can take this code right here. We actually need to go up to here and remove this because it's referencing the wrong arm state. And we want to set this to state. Okay, so now what this is going to do, and we want to say wait, we say double wait time. So now what we can do is we can set this here to wait time. Great. So now instead of having to do these lines of code here, every time you want to move the arm to a position, you can just call this. You can say set arm state. And in this case, we want to say low basket, right? And then we want to wait 1,000 milliseconds. Now we can delete this and it'll do exactly the same thing, except it does it in one line of code, right? And then at this end over here, after you've done the deposit with the intake servo, we can just set it back to collect sample. And the wait time will be the same because it's flipping it down. So you can see how that type of using methods for any amount of duplicated code, you can see even for this, it's only 5 lines of code or 6 lines of code. But when you have to use it like 8 to 10 times in your auto, it's going to really add up. So it makes a lot of sense to create a method for it that you can input the target state and the wait time in this case, and then just call that where you need it and save a lot of space in your codes. It means you have no duplicated code, makes it much easier to read, makes it much easier to fix, just shortens your program in general, and it's very useful. So that about wraps it up then for the auto. I did go through it quite quickly in this one compared to what I did with the Go Builder one, but I think that's fine. If I did explain the driving and stuff too fast, then go look at the Go Builder third session on the driving, or you can also have a look at the Ignite programming training sessions. Probably 3 and 4 would be quite helpful. But yeah, that about finishes it for this session. So thanks so much for watching, and I hope this was helpful.